Right now, somewhere in the universe, a star is disappearing into a black hole. For decades, we believed we knew what happened next. Everything was destroyed. But physics says that should be impossible, because according to the laws of nature, information can never truly die. Not a single atom, not a single photon, not a single memory. If black holes destroy information, why does modern physics insist that information cannot be destroyed? Stay with me, because by the end of this journey, black holes may no longer look like cosmic graveyards. They may be where the universe keeps its memories. Imagine throwing an encyclopedia into a fireplace. The pages curl, the ink vanishes, the paper becomes ash, smoke rises into the air. At first glance, the information is gone. Every word, every image, every fact, destroyed. But physics tells a different story. Nothing was actually erased. The information still exists, hidden within the motion of trillions upon trillions of atoms, scattered through the smoke, the heat, the ash. If you possessed enough knowledge and enough computing power, you could reconstruct every page perfectly. The entire book is still there, just scrambled beyond recognition. And according to modern physics, nature works exactly the same way. Information can become impossible to read, impossible to recover, but it cannot simply disappear. This idea sits quietly beneath almost every law of physics, and for a very long time, nothing seemed capable of breaking it. Then humanity discovered black holes, and suddenly the universe appeared to have found a loophole, a place where information seemed capable of doing the one thing physics said it never could: disappear. Imagine pouring lemon juice, pineapple, ice, and sugar into a blender. You turn the knob, the blades begin spinning, the ingredients mix together. You expect a refreshing mocktail, right? But what if instead of taste, instead of flavor, instead of the drink itself, all you got were three labels: mass, charge, spin. Nothing about the sweetness, nothing about the pineapple, nothing about the recipe. Everything that made the drink unique, gone. As absurd as that sounds, that is remarkably close to how black holes behave. A star can fall in, a planet can fall in, an asteroid can fall in, even an entire civilization could fall in. Yet from the outside, after all that complexity, only three things remain: mass, charge, spin. Everything else disappears behind the event horizon. Physicists call this the no-hair theorem. A black hole appears to have no memory of what it has swallowed. At least, that is what it seems. And if that were truly the whole story, information would be dead. Yet the universe wasn't finished surprising us, because black holes had one final secret: they weren't eternal. In 1974, Stephen Hawking made a discovery that shocked the scientific world. Black holes are not completely black. They slowly leak energy, particle by particle, year after year, trillion after trillion years. Imagine placing an ice cube on a table. At first, it seems permanent, solid, unchanging, but minute by minute, tiny amounts of water leave its surface. The change is almost impossible to notice. Yet given enough time, the ice cube disappears completely. That is essentially what Hawking discovered. Black holes evaporate, not quickly, not dramatically, but slowly enough that eventually they vanish. And that created a terrifying question. If the black hole disappears, what happens to everything that fell inside? Did the information survive, or did reality somehow erase it? Either information survives, or one of the foundations of modern physics is wrong. And neither possibility was comfortable. So physicists began searching for a third answer. If thoughts like these are starting to shift how you see your own past, stay with this journey, because what comes next goes even deeper. Think about a zip file on your computer, a 500-page book, thousands of photographs, videos, documents compressed into a tiny icon. To someone who cannot unzip it, the information appears gone. Yet every detail remains hidden inside, not destroyed, repackaged, encoded, compressed. And then physicists began wondering, what if black holes are doing something similar? Not with software, not with computers, but with reality itself. Perhaps information is not being destroyed. Perhaps it is being compressed into a form we cannot yet understand. And nature already gives us examples of compression far more astonishing than any zip file. A single fertilized egg contains the complete instructions to build a human being. Every organ, every cell, every neural connection, all compressed into something microscopic. Complexity hidden within simplicity. Black holes may be performing the most extreme version of that process in the entire universe. Not destroying information, compressing it, encoding it, preserving it. But where? The answer may lie on the very edge of reality itself. Imagine watching a three-dimensional movie. Characters move through space, cities stretch toward the horizon, entire worlds appear to exist in depth. Yet everything is actually encoded on a flat screen. A two-dimensional surface creating the illusion of three dimensions. As impossible as it sounds, some physicists believe the universe itself may work this way, because the information inside a black hole appears to scale with its surface area, not its volume. That should not happen. Almost everything in our everyday experience scales with volume, but black holes follow different rules. It is almost as if information is written onto the event horizon itself, like words carved into a cosmic wall. This idea eventually evolved into one of the strangest concepts in modern physics, the holographic principle. The possibility that all of three-dimensional reality may emerge from information encoded on a lower dimensional boundary. And if that idea is correct, then black holes are not the strangest objects in the universe. The universe itself is. Perhaps we have misunderstood black holes from the beginning. Perhaps they are not cosmic trash bins. Perhaps they are archives. When something falls into a black hole, it may not disappear. It may be compressed, encoded, preserved. The book is gone, but every word remains, archived in a language we do not yet know how to read. And perhaps, one day, we may learn to decipher that language, to read the history hidden inside black holes. Stories of stars long gone, galaxies long vanished, secrets preserved for billions of years. And if information truly can never be destroyed, then every black hole in the universe may contain a record of everything it has ever consumed. Not as matter, not as light, but as memory. And if this made you see black holes a little differently, stay with me as we continue exploring the mysteries hidden inside space, inside time, and inside the invisible laws that shape our universe. Take care. Shannon Raj here,